Hello, I'm Marshall Wise, Systems Engineer and leader of the modeling team at PNNL's Joint Global Change Research Institute in College Park, Maryland. It's my pleasure to present on behalf of the GCAM team a high-level overview of our Global Change Analysis Model, or GCAM, and its most recent release version coming in July of 2021, version GCAM 5.4. I'll give a summary of the coverage, the scope, and resolution of the model, as well as a discussion of its modeling and solution approach. Other videos in this series will focus on procedures for installing and running GCAM, as well as more details about technology representations in specific model sectors. GCAM, which is now in release version 5.4, is a multi-sector model of human activities, their economic and physical interactions, and their feedbacks with regional and global energy, agriculture, land, water, and emissions of greenhouse and other gases, ultimately with a link to global climate. GCAM is a long-term model in that it typically is run to the year 2100, providing regional and sectoral scenario results in 5-year time steps. GCAM is built and maintained by PNL at the Joint Global Change Research Institute. It's been available for several years now as a community model with users in several countries, and it has benefited from several collaborations from partners outside of JGCRI. Finally, GCAM is the product of decades of development of modeling of energy, land use, and emissions at PNL. GCAM provides a platform for exploring the interactions among multiple human and Earth systems. This figure illustrates the major sectors and components GCAM represents, along with examples of feedbacks and multi-sector dynamics among these. GCAM provides a quantitative, fully internally consistent representation of these sectors and their interactions. For example, consider the multi-sector factors involved in bioenergy demand and supply. Energy demand is driven by socioeconomics as well as climate, and bioenergy demand is determined by its economics relative to other energy resources, which of course can also be affected by policy incentives. Bioenergy production, at least in the form of dedicated bioenergy crops, involves an economic competition for land with food and fiber crops, whose demand is also driven by socioeconomics. And the scarcity of land is also affected by the yields of all crops, which is influenced in turn by technology and climate. Finally, the production of crops requires water, which is also demanded by the energy system and other human activities. And this is just one example of the multi-sector dynamics that must be considered. Although GCAM is a complete, self-contained model that runs independently, it also serves as a central integrating model for the GCIMS suite of data and modeling and analysis tools. The GCIMS, or the Global Change Intersectoral Modeling System, is our large science-focused area project with the U.S. Department of Energy's Office of Science. These tools in the suite include data processing tools that take raw inputs like energy and land data to produce GCAM model inputs. There are also single physical system models, such as the Hector climate model and the Xanthos hydrology model. And there are results disaggregation tools and dynamic emulators as part of the GCIMS suite. The GCAM 5.4 released model contains the set of tools shown here. From the left, the GCAM data system, which is an R package and database, which takes in data from sources such as the IEA for energy, the FAO for agriculture, along with assumptions and parameters, and creates the GCAM input data that the model uses to run. The release contains the GCAM core model itself. The release also contains the Hector Earth System and Climate Model. And it also comes with GCAM USA, which represents energy at the 50-state level for the United States while running inside the global GCAM. GCAM provides global coverage with flexible regional resolution chosen as a balance between tractability and utility for analyzing key questions. From the left, and as seen in earlier slides, the energy economic systems are modeled with countries aggregated into 32 regions. Each of these regions contains a complete representation of energy supply and demand. GCAM has 235 water basins modeled around the globe for balancing water requirements within those basins. And there are 384 land use regions, which are modeled based on the combination of the 32 energy regions and the overlapping water basins. So each land use region contains a complete representation of agriculture, natural lands, and terrestrial carbon. The regional scale is flexible, though, and can be defined by data, but it requires some level of research and effort. It's not something that's completely automatic, that we have tools that help that. The example of GCAM USA is shown, but there have been other sub-regional versions created by collaborators for some other parts of the world. Okay, this figure shows an overview of the sectoral coverage of GCAM. On the left are the inputs to the model covering energy and other resource bases, land resources, and technology assumptions for converting these resources to meet demands. And following down the left side are the socioeconomic inputs that drive the scale of demand, as well as technology characteristics for providing energy services such as transportation, buildings, heating and cooling, and industrial energy. The middle columns show the components of the GCAM model itself. Here, energy, land, and water resources are produced and converted to meet demands for energy and food and fiber and forest products. In between supply at the top and the demand at the bottom is the marketplace, which solves for prices and trade in each modeled product to clear markets and allocate constrained resources in an economically efficient manner. From the production and use of energy and land and other activities, emissions of CO2 and several other gases and pollutants are computed by GCAM. Now, on the right side is a summary of the outputs of a GCAM run. These outputs are computed for each region and for each model period. They include production and consumption of energy, agriculture, and water, prices of all these products, trade, land use, and emissions. You may wish to pause this video to look over some of the details before going on. Many economic choice decisions in GCAM are based on a logit approach, in which we implicitly assume that there is a distribution of costs or profit rates rather than a single point estimate for different options. The market share then is based on the probability that a technology option has the least cost. From the example in the figure, there are three technology options with increasing median costs. However, there's an overlap among the distributions where each technology option has the lowest cost. And in this example, option 1 will receive the highest share, option 2 the second highest, but even option 3 that has a much higher median cost still receives some share. Note that this approach results in a nonlinear competition. It avoids the winner-take-all result where one slightly cheaper or slightly more profitable technology captures the entire market unless physical constraints are placed on it otherwise. The logit approach also allows us to calibrate historical choice preferences by algebraically solving for share weights, as shown in the formula there, that reproduce historical data. A few notes about GCAM's solution process for finding economic equilibrium. GCAM solves each period by searching for the set of all prices so that supply equals demand for each modeled market. GCAM models this equilibrium in energy, agriculture, land, fertilizer, water, and emissions markets. International trade is resolved as part of this equilibrium for each of the markets. This approach is often referred to as a dynamic recursive solution. The flow diagram on the left simplifies this process to its bare essentials. First, you start with a set of prices for everything, then run GCAM for a period. Then you test to see if supply is equal demands, which will likely not be the case on the first attempt. So if not, GCAM uses mathematical methods to try to get a better set of prices to try for the next iteration within that period. This involves running markets with perturbed prices to compute derivatives as well as some other mathematical techniques. Now, when all demand and supplies are equal within a solution tolerance, the period is considered solved and you move to the next period to solve it. Finally, we want to finish this overview by stating an important point about how to interpret GCAM results, and that is that GCAM results are a function of scenario input assumptions. You can get very different results depending on the values chosen for input socioeconomic drivers, technology assumptions, resource bases, and policies. In doing GCAM studies, it's important to understand and document assumptions along with results in order to be able to present a complete understanding of the implications of the scenarios. Now, with that final note, we thank you for your attention and encourage you to explore other videos and resources such as contained on the link shown below. Thank you.